In this video, we'll see how Interactive Configuration Explorer can be used to analyze large categorical parameter spaces based on their impact on a dependent numerical variable. In this example, this is ICE working on a system's performance dataset, and the variables in the dataset are shown as green buttons, like workload file system. Each of these variables have several levels, which are shown as labels underneath the bars, like database server, file server, are labels for the variable type workload. The three views of ICE can be seen on the screen. The parameter explorer view is between these two throughput bars, and it helps in quick filtering of this large parameter space. As we can see, the user can readily correlate all of these parameter levels by just looking at the throughput distributions and the statistics. The view on the right of this throughput bar is the aggregate view, which shows the aggregate impact on the target variable, which is the throughput in this case, based on a configuration selected by the user in the parameter explorer view. And underneath both of these views is the timeline view, which keeps track of the changes in the range of throughput values for each user interaction. Moving forward, now we talk about the first use case of ICE tool, which is how to compare different parameter levels based on this parameter explorer view. Consider a system running a database server workload. As we can see, such a system has very high range of throughput values, but the throughput values on the upper part of the distribution are greater in number than those of lower part of the distribution. So this shows that even if the range of throughput values for a database server workload is very high, but the probability of ending up with high throughput is greater than the probability of ending up with lower throughput values. Now, if we compare database server workload to file server workload, we can immediately see that the overall throughput range, as well as the maximum throughput values for file server workload, are very low compared to the one with database server workload. Also, we can see the differences in the distribution, where the distribution of file server workload is almost like bimodal, but very similar on the opposite ends. But the distribution for the database server workload is highly tailed, with more number of data points on the upper end as compared to the number of data points on the lower end. In this way, ICE tool can be used to compare two parameter levels for quick correlation and comparison. Next, we move on to the second use case of ICE tool, which is the filtering of this large parameter space to find the right set of configurations based on an objective. In this new example, let us assume we're trying to optimize a system running a database server workload based on two objectives. One is to reduce the variation in the system performance, that is the range of throughput, and another objective is to get the throughput value as high as possible. To follow this objective, we can select the database server workload on the parameter explorer. Now we can see for file systems, we get these new distributions, and it is clear from these ranges that choosing the file system XFS would give me minimum range as compared to all other file systems. So let's choose file system XFS. After choosing XFS, we can see that A-time option none has even lower throughput range, but we can see that the highest throughput value has decreased. It can be verified from the timeline view, which shows this red line going lower and lower with each of these filtering steps. And this blue line comes closer to the red line, which shows that the range of throughput has decreased, but at the same time, the maximum throughput value has also decreased. So if we try to find a better configuration, we can roll back to the previous stage by clicking on this timeline view and again find and again do the search for finding new configurations which don't decrease the maximum throughput value, and we can maybe compromise on range of the throughput. Continuing the search for a good system configuration with high throughput value and low performance variation. This time we can choose the file system ext4 as it has the highest throughput value compared to all other file systems. After choosing ext4, let's look at all of the other variables and see which variable would not not decrease the highest throughput value but would reduce the range of the throughput. So it can be seen that the journal option ordered has the same highest throughput value, but it has the lowest range for the throughput performance as compared to all other parameters on the plot. So we'll go ahead with journal option ordered, and the timeline view confirms that the range of throughput has considerably decreased from the previous steps. Now moving forward, we can choose device type SSD, which would reduce the range further, but the highest throughput value still remains the same. Let's choose device SSD, and from now on we can see that every other parameter level has the same or the lower highest throughput value. So now we are stuck at a trade-off that if we want to have the highest throughput value being consistent, we would stop at this configuration. But if we want to lower the range of the throughput further, we can choose IO scheduler CFQ, which would reduce the range of the throughput. At this point, we can compare the results from the two configurations that we chose. The first configuration is this left part of the timeline view, which can be traced back by clicking on the final position in the timeline for configuration 1. As we can see, the range of the throughput values is very low for configuration 1, but the highest throughput value is compromised. On the other hand, if we see our resulting configuration 2, the throughput range in this case is greater than the throughput range in configuration 1, but the highest throughput value is not compromised. So using ICE, we can do multi-objective filtering and get the resulting configurations based on the user interests.